of Yale University. He trained for medical school and residency at Columbia, and then went on to Yale for fellowship, and is currently associate professor and medical director of the labor and birth unit there. He has won multiple accolades throughout his career, including multiple teaching awards, and is known for taking very difficult subjects and breaking it down into very palatable portions. He has had over 40 peer-reviewed articles, along with multiple other reviews, and is very well respected by peers, trainees, ancillary staff, pretty much anyone who's had the pleasure of working with him. So at this point, I'll turn the mic over to Dr. Pettker to talk about basic biostats.
Great, so this is the first lecture for the biostats section. There will be one or two more, and this is meant to be a very basic introduction to biostats and breaking it down into very simple forms. And hopefully you'll find this helpful when you're reviewing papers, when you're putting together presentations. I'm going to start by saying I have no conflicts of interest to declare. And the objectives are going to give an overview of very basic terms and concepts and review how to apply our basic biostatistical tests. We're going to focus on concepts, not calculations. It's not important for us to know how to derive the variance or how to run SPSS or anything like that. And we're going to come up with some concepts to help you review papers when you're for the green journal or the gray journal or the other journals that we review for. And hopefully it's going to help you write papers and come up with your own research results in helping you decide what tests to use. So very practical talk today. Three basic assumptions we're going to have at the beginning of this talk. Statistics are only helpful if you use the correct ones, so we're going to emphasize how to use the correct ones. The correct test must be based on the correct assumptions of the data, so we can apply these tests when we make the correct assumptions of the data. Is it normally distributed or parametric? So do we apply a parametric test? Is it non-normally distributed? Is it nominal data versus ratio data? That will help us choose the correct tests. And then when we're writing or reviewing papers, we need to check those two facts to make sure we're doing the right thing. So I came across this book preparing this talk at our library. It's from the 1930s, Maternity Care in Pictures. And it's an informative book with pictures for expectant mothers. The doctor is specially trained to care for mothers and babies. The doctor examines the abdomen and pelvis and takes careful measurements. And then a complete examination omits no detail. And the concept is that for the mother, safe maternity care begins with the selection of a competent doctor before the third month. And in the same way, when we're applying our statistics, safe statistics begins with the selection of appropriate methods before the analysis. So I'm going to focus a lot on what we do before we analyze the data rather than what we do after or when we're analyzing the data. So we have two basic types of principles in statistical analysis. There's describing and then there's testing. And half the battle when we're doing statistical analysis is describing the data. So actually a lot of my talk is just about what are descriptive statistics. This isn't really work that gets you published and gets you famous, but it's critical to how we approach the data and what we end up with. So describing the data is really important. It identifies the patterns in the data, it identifies the outliers, and it guides the choice of which statistical or inferential statistics we're going to use. The inferential statistics are what we do to test and compare and to judge the data and to make conclusions about the relationships and the significance. And so descriptive statistics allow us to generate hypotheses, and the inferential statistics allow us to test those hypotheses. And first, when we're dealing with a data set, the first thing that we need to do is approach describing it. So descriptive statistics are measuring one variable, and the fancy term for it is univariate analysis. If you don't want to keep it so simple that you're just talking about descriptive statistics, you can use the fancy term univariate analysis. So we have to break our data up into what does the data look like, or how is the data grouped. So we have four different major categories, and the top two and then the bottom two are grouped into categories together. Nominal and ordinal data are generally grouped together, and interval and ratio data are generally grouped together, and you'll see why in a couple of slides. So nominal is just what that means, named categories. There's no particular order and no associated values. That would be blood types, O positive, A positive, A negative, sex and gender, alive versus dead. Numbers on player uniforms are also nominal. They might be numbers, but they're no particular order, no associated values. Number 8 doesn't necessarily mean what number 8 does in most sports. Some sports it's a little bit different than that, but most sports the numbers don't matter. Whereas ordinal data are somewhat nominal, somewhat named, but they're ordered. They're differences, and the differences are grouped in terms of ranking. So stages of cancer are a great example of that. You have stage 1, 2, 3, and 4. 4 is not necessarily twice as bad as 2, but they're ordered. 4 is worse than 2. Honors, pass, fail in our medical school, and personal health status. There's not necessarily a ranking or a ratio difference between excellent, very good, and good, but there is a difference, and there's an ordered difference to it. So that's what ordinal means. And then we have interval data. Interval data are generally numbers, and there are equal distances between the ordered categories. So clock time, Fahrenheit scale for temperature. Fahrenheit scale doesn't have an absolute zero, and 60 degrees is not twice as hot as 30 degrees, but 31 degrees is one more degree hotter than 30 degrees. And then BMI and IQ. BMI doesn't have a zero. There's nobody with zero BMI, and IQ as well. Whereas ratio data is numerical. It has equal intervals, and there's a meaningful 0 point. So the difference between Fahrenheit scale for interval data, the application would be Kelvin scale, where there is an absolute zero. Zero does mean something for temperature in the Kelvin scale. Time and age, weight, and hemoglobin. So this is ordering the data into types of data for descriptive data. So nominal and ordinal are generally grouped together, and then interval and ratio are generally grouped together. And this is just a visual description. Nominal data are names of things, and the names don't necessarily mean that one is more important or less important than the other. Ordinal does mean that the names or numbers do have ranking. Interval data is the intervals between the data points are important. And then ratio data, there's a zero that's important. And now these data can also be described a little bit further, particularly ratio data. Continuous ratio data is a data with infinite numbers of measurements, like temperature, height, weight. Or you can have discrete numbers. There's a finite number of measurements. So you can have that with nominal or numeric data. You can have 1, 2, 3, 4 through 10, and it doesn't have to be continuous data for it to be interval data. Or you can have that when we talk about categorical values. So you can have dichotomous categorical values like hot and cold, male or female, or non-dichotomous, which would be nationality. So dichotomous would be 1 versus 2, and non-dichotomous would be 1, 2, 3, 4, 5. And then we have various types of measures. So when we're taking measurements from particular observations, we have independent, paired, or clustered measures. Independent measures are when each observation is from a different subject. So if we talk about an induction trial and we're looking at the observations of time to delivery from beginning to cervical ripening, each observation in that case is from a different subject. Whereas we could have another type of study where we're looking at paired data when you have two observations from the same subjects. So this would be something where we measure a weight before an intervention and then a weight after an intervention, and those would be paired data points. And then clustered would be multiple observations in each subject. So looking at multiple observations in somebody's weight over a period of time would be clustered data. And it's really important that we apply all of these names to the data as we collect it and as we group it once we're done with our study so that we know exactly what we're dealing with. So this is to help us understand what type of data is most useful and most amenable to analysis. So we have to know if it's interval data or if it's ratio data or if it's ordinal data versus nominal data. That helps us apply what the type of analysis and the type of tests to the data that we have. And there are always exceptions. And it's important to know the exceptions and how to apply the exceptions. But when you're applying the exceptions, you have to know why you're doing that. And you have to have a good reason for doing that. Otherwise, and I think this comes up a lot when people are submitting papers, if they don't know why they're applying it and they don't know the exceptions, then they get pointed out by the reviewers and they have to go back to the drawing board. So this is a really nice visual of why this data is important and describing the data is important when we get to the point of analysis, because the type of analysis that we apply will really depend on how we describe the data. So nominal and ordinal data has qualities to it that make it make us have to analyze it using non-parametric statistics, and we'll get to the difference between parametric and non-parametric in a little bit. But this is qualitative data, and it's not numeric or continuous data, and it's a little bit harder to analyze with numeric statistical analysis. So we usually have to apply non-parametric statistics to nominal and ordinal data. Whereas interval and ratio data, we can apply parametric statistical tests to it and get a higher level of information and inference from that. You can also use non-parametric tests for interval and ratio data. Doesn't mean that you can't use those types of data, but you can't use parametric tests for nominal and ordinal data. And as a reviewer, when I see that happening in a paper, then that's a time where we might need the authors to go back to the data and reanalyze it in a more trustworthy fashion. So applying the right test is important when we look at the data this way. So when we look at our descriptive statistics, or when we start to get to the analysis of descriptive statistics, we are trying to find basic features of the data. So it provides summaries, patterns, and outliers, and we're going to look at centrality, variation, and frequency. And again, this is stuff that we learned in high school and even before high school, like means and medians, but it's really important that we go back to looking at this, because this is, we have to be very sensitive to what the data looks like when we're choosing the types of tests. The optimal measure depends on the type of data being described. And again, we're not talking about inferential statistics. This beginning of this talk is just descriptive statistics. So looking at the data can be very helpful. So I tend to really like to look at the data and what it and this graphical description of the data can really help us figure out what the next steps will be when we analyze the data. So different ways of looking at data graphically. We can use a bar graph, and we usually apply a bar graph to nominal or ordinal data. And in a bar graph, it's really important when you're looking at a bar graph that there's spaces between the categories. So you can see in this example, we have 4 categories and there's spaces between the category. And this implies visually that it's non-continuous data, that the data is not next to each other. It doesn't necessarily have a relationship. And that's different than a histogram. And a histogram is usually ratio or interval data. There are no spaces, and that implies that there's a continuity or a relationship between the categories along the x-axis. And that's important for us to keep in mind. A bar graph is not a histogram, and a histogram is not a bar graph. And then we have a frequency polygon, and a frequency polygon looks a lot like a histogram, but it's usually for interval data. There might be there might not be continuous data. There are discrete data points, and it doesn't imply that we have continuous data. And it allows us to display multiple variables, and it just gives a smoothness to the look. But you couldn't describe nominal or ordinal data with one of these frequency polygons. That would be a misrepresentation of the data, that the data um, at one measurement has a relationship to the data at the next measurement. So even just graphing these things out can be really important. And here's one example, a very famous example of, let me scoot that up a little bit, a very classic example of the power of descriptive data. This is John Snow's map of London during the cholera epidemic. He was an epidemiologist. He's sort of the father of epidemiology, and this cholera study really points out how this was done. So he was trying to find patterns in the cholera epidemic because he was noticing that maybe there were clusters of cholera in different locations. And just looking at this data, if you look really closely at it, there are bar graphs superimposed on a geographic landscape. And the bar graphs indicate how many cases of cholera there were at each address. And what this demonstrates is that there's a clustering around the center here of cases. And this allowed him to say, hey, this cluster is associated with one water pump within this location in London. And that enabled them to figure out where the source of the cholera epidemic was at this time. So this is how descriptive statistics can be very powerful. The second example of where graphing descriptive statistics can be very helpful is in Napoleon's Russian campaign from 1812. And this is lifted from an author named Edward Tufte. If anybody's heard of Edward Tufte, he's a statistician who um, is enamored with the visual display of quantitative information. And his classic book from the 80s is the visual display of quantitative information. He points out this Napoleon's Russian campaign. And this is a really strong graphic that demonstrates that you can put descriptive data into a form that is so descriptive that it gets the point across without even having to do any analysis to it. This is a descriptive graphic that shows Napoleon's Russian campaign from 1812. And as you go across left to right, it's using geography as well as, and so the march to Moscow during 1812 of Napoleon uses the geography as well as it has a placement of dates along it, and the troop size is getting smaller. That's the width of those bars as we go along through the march. And he gets to Moscow in the winter of 1812, and he's forced to turn around because his troop size diminished so greatly. And then along the bottom is a graph of the temperature. So on this one graphic, we have dates, army size, geographic troop location, the direction of troop movement, and temperature. And it's very descriptive to why this failed and what Napoleon was left over with at the end on his retreat, with the retreats in black. So don't underestimate the power of descriptive statistics, and especially the power of mapping or graphing your descriptive statistics when you're looking at your data. It can be extraordinarily powerful. So we can communicate describing the data and most of the stuff that we do by graphing it in histograms and bar graphs, and we can communicate that visually, but how do we communicate that in terms of the numbers and the qualities of the data? So first we look at central tendency. Measures of central tendency are our mean or our average, our median, and our mode. And the mean is generally called the average. For instance, if you're looking at, or if you're using Excel on Microsoft, there's no function for mean. You have to use the term average, and that's your X bar. And that's the most common measure of centrality. And it's really informative when the data follow a bell-shaped curve or when it's normally distributed. In fact, it's only useful when we have normally distributed data. The median is the middle value, or the 50th percentile, and half of all the observed values will be smaller and half will be larger. And when data are skewed, or when it's not bell-shaped or normally distributed, this is the better measure of centrality, median. And then the mode is the most frequently observed value, and this is generally used for nominal data, so data that's not interval or ratio data. You can have more than one mode in a data set. You can't have more than one median or mean. And you would use this for nominal data. And so you can see here that even when we're just starting with measures of central tendency, it's really important for us to figure out what type of distribution we have for the data and what the description, the original description of the data was. Is it bell-shaped or skewed? And what choice of central tendency we're going to use to describe it. And I use this for when I'm looking at papers to review to see if the authors are really, if they know their data set very well, and are they using the appropriate measure of central tendency. So are they reporting mean or median, and have they done the right look at the data, and are they making the right assumptions? So here we have the graphical display of mean, median, and mode. So when we have something that's bell-shaped, the mean, median, and mode are generally right about the same. But if there's skew to it, like in C on the lower left, the mode, the median, and the mean will be different. And when we have skew like that, the median is actually the more trustworthy measure of central tendency to use. And then when we have data that has two modes to it, we might get tricked that the mean and the median are the same, but it has two modes. So graphing data like that can be very helpful. And let me just go back a bit, because it's really important for when we're talking about normally and non-normally distributed data to know the tests that we do to determine this. And this would be one of the tests that you do when you are feeding your data through your statistical calculators and trying to figure out what tests to do. The Kolmogorov-Smirnov test, or the KS test, is how you would determine whether something's normally distributed or non-normally distributed. So you would report when you're writing your study up, you would report that we did an analysis using the Kolmogorov-Smirnov test, and we determined that the data was normally distributed. And for normally distributed data, we report the mean. And for non-normally distributed data, we report the median. And that would be a really open and honest way to report your data. So you have measures of central tendency, and then you have measures of dispersion, or how closely the data cluster around the mean or median. And we have, for this, generally we use range and standard deviation. Range is the maximum and the minimum that we're reporting. It can be the highest and the lowest, or most commonly we report the interquartile range, or the IQR. And this would be the middle 50% of values, or the 25th and the 75th percentiles. And this is generally what we report when we're looking at non-normally distributed data. We use the range because it's less affected by outliers and extremes, and we generally report the interquartile range. So just going back through things, we would say we applied the Kolmogorov-Smirnov test. We found that this data was not normally distributed, and so we are reporting the median and the interquartile range. Whereas if our KS test told us that things were normally distributed, we would report the mean and then the standard deviation. And the standard deviation is just a function of the average of the deviations, or x, of each observation from the mean. So we start with the variance, which is a calculation that I don't want anybody to try to remember, but it's the average value of the squared deviations of each value of the mean. So the x squared summed averaged across all of the measurements. And the standard deviation is just the square root of s, or of s squared, so it's just s. And that's generally what we use to report for our normally distributed data. And then the difference between standard deviation and standard error of the mean is that standard error of the mean is the variability that's expected when measuring the mean from different samples. And this is an inferential statistic that really depends on sample size. So standard deviation is what the actual data says, whereas the standard error of the mean is from different samples and depends on sample size. And then finally, for measures of dispersion, when things are non-normally distributed, the symmetry of the curve can be described in skewness. The left-sided tail would be a negative skew. So we'll get to that in some visuals I have in a second. So why does this matter? Why does mean or median matter? Well, we can have two data sets, group 1 and group 2, that look very similar. We can have a group 1 data that looks very similar, has basically the same numbers except for the last value, 20 versus 10 for group 2. They'll have the same median, but they'll have very different means. There's more skew to group 1 rather than to group 2. The standard deviations for group 1 would be 6.1, whereas for group 2 it would be 3.2. And so group 1 data is being very affected by that one outlier of 20, whereas the group 2 data is more, has less dispersion to it. The two have very similar interquartile ranges, or exactly the same interquartile ranges. Somebody's moving my slides. Hold on. There we go. And when the data sets are small, we can see in these two data sets that there's a single extreme observation will have great influence on the mean, but little or no influence on the median. And the median is usually more informative for centrality in these small data sets. So if the mean is influenced by a single extreme observation, which is what we assume when the data is non-normally distributed, the standard deviation will overstate the actual variability. So we don't use standard deviation in those cases. It's better to express it in range. So when we have skew, or when we have something that's dispersed in a non-normally distributed way, because the standard deviation can be so affected by one or two outliers in a small data set, we tend to use median and a range. So here's a more graphical representation. When we have something that's normally distributed, the mean, median, and mode are generally the same. There's zero skew or very little skew to the distribution. And then we can assume that 68% of values fall within one standard deviation and 95% of values fall between two standard deviations. And these 4 points are the definition of normal distribution. So a normally distributed data set fulfills these 4 points. And when we have something that's normally distributed, we can analyze that data for inferential statistics using parametric analysis. That's as opposed to data that's skewed when the median, mode, and mean are not the same, and we can't apply standard deviations. And this is when we need to use non-parametric analysis. So this would be when we use a median to describe the data, that would be a more accurate way to describe the data, and ranges would be more accurate to describe the data. So here we are again. We have normally distributed data and non-normally distributed data. So I used those two terms, parametric and non-parametric, assuming that the whole audience knows what the difference between parametric and non-parametric is. And these are terms that are often used, but it's really important that I don't assume that you guys all know what this means. Basically, the essential essence of parametric statistics are that they assume that something's normally distributed. You can only apply parametric statistics if you have a normal distribution. If you apply parametric statistics to something that's non-normally distributed, it goes beyond the assumptions of the data set, and the analysis that you do won't be accurate and won't be fair to the data set. Whereas non-parametric statistics don't make assumptions about that distribution. The thing about nonparametric statistics, it's not just that you have to apply them to non-normally distributed data, but you can apply nonparametric statistics to normally distributed data. It just is not as tight an analysis, and you will not necessarily get significance when you see significance. And generally, the nonparametric statistics are just rank tests. They're not. So when you see something called a rank test, that's generally a nonparametric statistic. And again, the test for looking at something, if it's parametric or if it's to have parametric versus non-parametric analysis, would be the KS test or Kolmogorov-Smirnov test. And that's a really important test to know about. It shouldn't be underestimated in its utility before we're starting inferential statistics. So again, parametric versus non-parametric. We have normally distributed on the left. We would apply parametric analysis, and we would use mean and standard deviation. Versus on the right, we have non-normally distributed data. We would use non-parametric analysis, and we would describe using median and range. The data, and so now we need to test it and choose the appropriate test. So after we describe the data, we have to formulate a hypothesis. We have to establish the null hypothesis and be as specific as possible with this. And I just put up an example here. There's no difference in time to delivery between Foley balloon and misoprostol for cervical ripening in nulliparous patients. So that's a null hypothesis. And we're testing that null hypothesis to see if there actually is a difference in a trial between I've just been told we've lost the audio. It seems to be working on my end. My microphone's going. Have we still lost the audio?
Dr. Pettker, we can hear you.
Okay, great. Somebody just texted me
Dr.
that they
Pettker,
lost the audio.
we can hear you.
Them. Yeah, great. Thanks. So, so the null hypothesis is assuming that there is no difference, and we're testing the null hypothesis to see if there actually is a difference. And when I say get as specific as possible, you hopefully did this before you started your study, that you didn't just look at a really general statement, that you got very specific in terms of the population, in terms of the measurement that we were doing, in terms of the comparators. And then we're going to determine what the data would look like. So when we look at that example right there, we're looking at time. And so that is ratio data that's continuous. And we're not necessarily assuming that it's normally distributed, but we would do that analysis to see what that looks like. And then we're going to establish the test or choose the test for proving or disproving the data. So univariate statistics are followed by bivariate statistics, and this is univariate is descriptive, and bivariate is when we start testing the data, and that's describing relationships between two variables. And variables are what we put in and what we get out. We have two types of variables, dependent variables and independent variables. Dependent variables are the outcome of interest. So the dependent variables are what depend on what we put in. And this is the changes or the outcomes that happen in response to our intervention. The independent variables are the intervention. That's what is being manipulated. And the phrase that I use in my mind that helps me sort these out is that the dependent variable changes in response to the independent variable. So the independent variable is what we're changing, and the result or the outcome that we're getting are the dependent variable, which depends on the independent variable. So our bivariate analysis will look at an association or correlation between a dependent variable and an independent variable. The dependent variable, again, is the outcome of interest, and it changes to the intervention, and that's usually put on the y-axis. And then we have the independent variable, and that's what we're manipulating. And there can be more than one independent variable, and that's usually on the x-axis. And we will look at the association or correlation between these two using a correlation coefficient. So our approach when we're looking at bivariate statistics are to choose what our dependent and our independent variables will be. And that's going to help us identify the type or direction of the relationship. Is it a positive or negative relationship? The strength of the relationship. Is it a strong or weak relationship? And then we can do a statistical test to find the statistical significance of this relationship. So when we're looking at correlation, the relationship between a dependent and an independent variable, the most logical technique, or the most frequent technique, is simple linear regression. And so we plug the dependent variable and the independent variable into our statistical calculator, and we get a result, a correlation coefficient out of it. So we run a linear regression in SAS or SPSS, and we get something called the Pearson correlation coefficient. And this is the estimate of the linear relationship or agreement between two variables. It can be a negative or a positive number. So +1 would be perfect positive correlation. 0 would be no correlation, and -1 would be a perfect negative correlation. So as the independent variable increases, the dependent variable would decrease. It assumes that there's a normal distribution of variances and that the variables are interval or ratio. So again, describing the data is really important, and getting a handle on what the data looks like is really important before we apply a simple linear regression. Probably the most useful statistic to come out of a linear regression is our R squared, though. And it's really important that we know the difference between R and R squared. So R is the correlation coefficient, and R squared is what we call the coefficient of determination. And that's the value of the relationship. Pearson is really sort of a strength and a direction of relationship. The R squared is the value of that. And so it's the degree to which the independent variable values explain the variation in the dependent variable. So let's say we plug in our linear regression and we get an R of 0.7. R squared would be 0.7 squared, which is 0.49. And the simplest way to describe what 0.49 means is that 49% of the variation in Y, or the independent the dependent variable, is explained by x, the independent variable. So that's what R and R squared means. When you see rho, which is the Greek for R, that means we're using the Spearman correlation coefficient, and that generally says that we're using a nonparametric test, or when the assumptions of normality between the variances and variables and whether or not we have interval or ratio data, when we're not making those assumptions and we apply a non-parametric test, we get rho. And the same assumptions or the same explanations for rho are possible, as we said, for Pearson. So rho is sort of the non-parametric equivalent of the Pearson correlation coefficient. So here's a graphical representation of what this means. So in the upper left, we have an R of 0.7. There's a direct positive relationship, and there's a pretty tight variance or less variance than what we have on the middle, where R equals 0.3. We have a direct relationship going left to right, and we have more variance. So that's why the R is not as high a number, but it's still a positive number. There's still a direct relationship. And you can see that the lines look very similar, but there's so much more variance that the correlation is to a lesser degree. Whereas if we go all the way to the right, we have no direct relationship, and the variance is kind of all over the place. And so that's an R of 0. So if we were to compare the R of 0.7 on the upper left to the lower left, an R of negative 0.7, there's a direct relationship on the upper left, and on the bottom left, there's an indirect relationship, and so that's what the negative would mean. They have the same variance, that's why the number is the same, 0.7, but they have a different direction of relationship. So this helps explain what the correlation coefficient means. And again, this is correlation and association. This is not implying causality. This is just things change together over a direction. Sometimes you can get nonlinear relationships. It's really easy when we have a linear relationship. We can apply linear regression to that. But sometimes we end up with nonlinear or curvilinear relationships. And it doesn't mean that we have to throw in the towel and we can't apply linear regression to these. We just might have to do transformations, like for this one in the middle, the nonlinear relationship, we might need to do a logarithmic transformation to make the data linear and to apply a linear regression to that. So we can still find correlations in these types of relationships. But again, this is hitting home why graphing the data and looking at the data can be so helpful. We look at this data here and we look at it, there is a relationship, it's nonlinear. What would happen if we applied a logarithmic conformation of the data, and if we conform the data to look linear by doing that transformation, then we could actually do a linear regression. And that's fair to do in the analysis. You just have to be really clear that's what you're doing with the analysis. So we can get significance from linear regression to see about testing the null hypothesis. So we just were looking at the strength of the correlation or causation. We weren't saying anything about the significance of it. The significance really depends on things we're plugging in to find significance. So it depends on the correlation coefficient, but even more than that, it depends on the sample size and the alpha and the beta that we choose. So our error acceptabilities of alpha and beta error, what we're plugging into our statistical calculator. So correlation coefficient is very important, but those three other factors are really what determine whether or not our data or the association is significant or not. So then we look at paired statistics, and this is the stuff that we see on a daily basis in the papers that we're reading. Paired statistics are the student t-test and the chi-squared test, and these are the most commonly used statistics that we'll see in the papers that we're reading. Continuous data relies on the student t-test. Categorical or grouped data will rely on the chi-square test. So student's t-test comes from, sometimes people are wondering, where does the student come from? It's not a guy named Student. It was actually William Gossett, who worked at the Guinness factory in Ireland. He was working on some statistical comparisons of some beer he was making, and he wanted to publish this data. He didn't want the data to look like it was coming from a beer drinker or somebody from the Guinness factory. So he published under the pseudonym Student, and then this test became popularized as Student's t-test based on that publication. This is when we're comparing two groups and when we're using continuous data. And it's calculating differences in the means and the variance amongst this data set. And this relies on normally distributed data. And so it's called a parametric test. And we can only apply student's t-test when the data is normally distributed. So we would look at the data using the KS test, and then we would apply student's t-test if the conditions, those four conditions of normal distribution were met. If we had non-parametric data or non-normally distributed data and we needed to apply a non-parametric test, we would be using a rank test like the Mann-Whitney U-test or the Wilcoxon-Rake sum test. And we're not going to go into the differences between those two, but those are non-parametric tests that would be the equivalent to using a student's t-test. We would use a paired t-test if the measurements are taken from the same unit or the same person over a period of time. And then this test will generate a p-value and a confidence interval. And that's what we can report in terms of reporting whether or not our results are significant. There's often a question whether or not we should apply a one-sided or a two-sided test. Our statistical calculators will ask us whether or not we're going to apply a one-sided or two-sided test, and it's really important to consider why it might be important to do one or the other. A one-sided test or a one-tailed test would be testing a directional hypothesis, and statistically it's a little less stringent. So an example would be looking at a treatment to prevent preeclampsia. So looking at aspirin to prevent preeclampsia in high-risk individuals, and not really caring if it actually might cause preeclampsia. So just assuming that, hey, this probably isn't going to cause preeclampsia. You would technically be able to look at that as a one-sided test. Or when evaluating a new drug for regulatory approval, we are only really going to take action if there's a positive effect. Negative effects are possible, but this would be the same as a zero effect. So when we're submitting this for regulatory approval, we might only do a one-sided test. A two-sided or two-tailed test is typically better. It's more stringent, and so you're going to have a higher bar to pass to get statistical significance. But this is a test that we would do when we care whether or not things are better or worse, and being better or worse has equal value in our analysis. When we're looking at dichotomous or binary data or non-continuous data, we can do the chi-square test. And we can actually look at continuous data using a chi-square test as well. We would just break things into groups. We would choose a cutoff and break things into groups. But usually this is when we're looking at frequencies, so 57% being affected, or the frequency of an outcome. This is when we set up our classic 2x2 contingency table, and the way that this test works is it compares the observed values to the expected values based on a Poisson distribution or a normal distribution, and you get out a p-value and an odds ratio. Two really important parts of this test: when we have one cell less than or equal to 5 in our 2x2 table, we have to use something called Fisher's exact test. That's a little more, it's a test that's more acceptable when we have a low number of values in one of the cells, and it accounts for the variation that can be caused by outliers from that. When we have paired data, we would use McNemar's test for paired data. And the chi-square test is a non-parametric test, so it doesn't matter if our values are normally distributed or non-normally distributed. This can be applied to any type of data set. So then next and finally, we can stratify our statistics. And so this is how we can look at we can group data and control for covariates. So you'll get a future biostatistics talk that will talk about how to do multivariate analysis. Stratified statistics are where we can take bivariate statistics and break them up to test for covariation. So we can stratify or break into categories within the range of values. We can create multiple 2x2 tables and then compare these 2x2 tables to each other to find a confounding variable or a covariate. And it's an example of how we can test for trends. And it's the simplest method to adjust for confounding during analysis if you can't really do it in design. So if you can't really do a multivariable analysis because of the study design for some reason, you can do this stratified analysis. And we often use stratification in randomized trials and also in other observational studies. And it's akin to multivariable analysis, but you can't control for multiple variables or confounders at the same time. So this would be something where you do a descriptive analysis, you see that there might be important covariates within your data set, and you want to test those covariates. So the relationship of trisomy 21 to advancing maternal age or birth order. When you look at the two graphs on the top, it looks like, wow, birth order and age both have an impact on the rate of trisomy 21. So cases per 1,000 live births on the y-axis, and on the upper left, birth order, and the upper right, age groups. So it's hard for us to determine which one is the covariate and which is the one that's the real dependent variable. Now, if we stratify the analysis, or we create these strata in the lower right, then we can tell that, hey, maybe it's not birth order, because birth order across each age group doesn't show very much variation. It really looks to be that the age is the factor or the influence on trisomy 21 cases. And so this is a real graphic representation of creating these strata, these stratifications, and helping us describe the data to see where the significance is. And so applying this kind of analysis shows us that it's age, it's not birth order, that birth order is a covariate with age, because as people get older, they have more babies. So the test that we would do for stratified analysis is the Cochran-Mantel-Hansel test. And this is breaking things into a series of 2x2 squares and comparing two groups and one outcomes and a covariate that it might be influenced. And so without getting into the details of it, we have a common odds ratio, and we compare the odds ratio or the relative risk for each strata, and we do a statistical analysis comparing all of these different strata, and we get a strength of association. So I have a couple of examples that show this, and a couple of obstetric examples that show how this is done. So our what's commonly known as the Meese trial, or the 17-OHP Caproid trial that influenced the use of 17-OHP Caproid for the prevention of recurrent preterm birth. What they noticed in this trial was that there was a very large proportion of Black women who were enrolled in the study. And a really important thing that they wanted to see was, was there a big influence of race, because there was such a high proportion of Blacks in the study? Did race influence the results in terms of the relative risk or improvement in the progesterone group versus the placebo group? So they did a stratified analysis using Black women versus non-Black women, and when you take out the Black women and look at their subgroup and compare that to non-Black women, there was not a statistically significant difference when we did that stratified analysis. When you look at the risk of uterine rupture during labor among women with a prior cesarean delivery, they did this same stratified analysis too. So this was an observational study that looked at the risk of prostaglandins, oxytocin, spontaneous labor, and the risk of uterine rupture. They stratified the analysis to look at no labor and patients with a rupture of uterine rupture in patients trying a TOLAC after a prior cesarean. They stratified the analysis to look at patients who had no labor versus spontaneous labor versus no prostaglandins but an induction versus induction with prostaglandins. And the stratified analysis allowed them to compare to the baseline group, make a comparison, and get a relative risk with a confidence interval. And using the Cochran-Mantel-Hansel test, they could see a statistically significant difference between the induction group with prostaglandins and a clinically significant difference in this group versus without labor. And this was a major practice changer by doing this type of stratified analysis. So nearing the end here, just summarizing what we talked about today in terms of how we approach the data when we get it. We're going to formulate a hypothesis, establish our null hypothesis, be as specific as possible with that, describe the data, continuous discrete, using the 4 groups of data that we might see. looking at the central tendency? Are we going to use mean or median and the dispersion around it? Is our data normally distributed? And then using those descriptions, establishing the right test for proving or disproving, and then performing the test. So these are some good resources just for general biostatistics for people. And I know the fellows are really hungry to learn more about biostatistics. And I would say that these books are good core books for people to use to get a good handle on biostatistics, particularly the Norman and Striner book. I think that it's well written, it's very simply done, and it breaks things up. This should probably be on every fellow's desk, and I have no relationship to the authors in terms of increasing their sales, but that's a really useful book, and it's something that over the years since my fellowship I found really handy for people. So I would steer people for that book if you're to buy one book. So I think we have some time for questions. I think Dr. Hahn's going to help moderate that for me since I'm new to this, although it might close in 1 minute because we're kind of on a new program here. I've been told maybe it ends at 1. So let's see how this goes.
So everyone can type in your questions in the chat box. In the meantime, just a reminder, this will be archived on our website. We'll also post a link on the Facebook group for those who are on the Facebook group. I see someone typing. We'll try to get this squeezed in before this kicks us out.
I don't see the typing, so Chris, you might have to read it.
Yeah, it said someone was typing and then it stopped, so it might have canceled their question. Any other questions? Okay, I think that might be it then. We're just about out of time. So thank you again, Dr. Pettker, and we'll look forward to seeing everyone again in a few weeks.